So today we'll be talking about some impossibility results for structuring preserved deterministic primitives. This is a joint work with Masayuki, Jan Camenisch, and Maria Dubovitskaya. In cryptography, as in many other areas, we often use the modular design principle. So complex cryptographic protocols are often built using building blocks such as encryption schemes, digital signatures, commitment schemes, and so on, to obtain the final protocol. And here, zero-knowledge proofs are often used to glue together the different building blocks by proving some relations among their inputs and outputs, and thus ensuring the correct work of the protocol. So, for instance, in the discrete log-based primitives, you have encryption schemes such as Elgamal, Camenisch. You also have Camenisch, Lisinski signatures. You have Pedersen commitments. And you also have verifiable encryption of discrete logs, verifiable random functions, and so on, that together with the generalized Schnorr proofs of knowledge, make it possible to obtain practical protocols for things like anonymous credential systems or oblivious transfer with access control, or group signatures, electronic cache, and so on. But the non-interactive versions of the Schnorr proofs are only secure in the random oracle model because they use the Fiat-Chamy paradigm to make it non-interactive. The good news is that in a great paper in 2008, Groth-Sahai introduced a practical non-interactive zero-knowledge proof system, or non-interactive proof system, which is secure in the standard model. But since it uses some bilinear maps to verify the statements, it has a limitation that the language is restricted to certain types of equations. In particular, for proofs of knowledge, we should have the pairing product equations, where the witnesses, AI and BJ, are source group elements, and the pairing product equation is basically a product of pairing operations raised to the power of some constant C. So I should highlight that these are not proof of knowledge for witnesses which are exponents. So you cannot just take Groth-Sahai proofs and use them as a replacement for the Schnorr's proofs of knowledge in the previous framework. We need to build building blocks which are compatible with Groth-Sahai proofs. So let's take a look at what we have with structuring preserved schemes. They use bilinear groups, and the public keys, inputs, outputs, are source group elements. And all the verifications procedures, such as verifications done during commitment opening phase, signature verification, or verification of the decryption correctness are done using pairing product equations. And by doing so, they are compatible with Groth-Sahai proofs of knowledge. So in the last couple of years, we have obtained some important building blocks, such as an encryption CCA secure scheme that's structured preserved by Camenisch et al. In Asia Crypt 2011. We have obtained also many signature schemes, as Groth just explained, and probably you have a good understanding there. And we also have commitment schemes that were introduced by Ab et al. But we still have to investigate which other kind of primitives can be obtained. In this work, we focus on deterministic primitives. So let's take a look at what kind of primitives we consider here. For instance, we have verifiable random functions or verifiable unpredictable functions, which instead of having only a secret key, as in pseudo-random functions, they also have a public key. The computation is done in the same way as the pseudo-random functions by taking an input x and the secret key and obtain an input-output y. But there is also a proof algorithm that takes in the input and the secret key produce some proof of the correctness of the computation. And of course, a verification algorithm that takes the input X, some output Y, the proof and the public key, and outputs a decision B. The requirements are the probability, meaning that every pair of correctly generated output and proof should be accepted by the verification algorithm. The uniqueness, meaning that for some input X, there should not be two output values Y and Y prime that both have valid proofs that would be accepted. And we also have the pseudo-randomness or unpredictability, depending on which functionality you are considering. That basically means that one adversary cannot guess the output corresponding to any input that was not paired to the computation and proof oracle, that he has access to both oracles. Or we consider also unique signatures, which are digital signatures where each message can only have one possible signature. And this leads us to the question, is it possible to obtain structuring preserve verifiable random functions, or structuring preserve verifiable unpredictable functions, or unique signatures? And the answer, as we prove in this work, is not with algebraic algorithms. So what are algebraic algorithms? An algorithm A that takes as input some group elements x1 up to xn and outputs a group element y is called algebraic. It has to know some representation of the output element y with respect to the input elements. Or in more detail, the algorithm A takes the group description, some inputs x1 up to xn, a string and some coins, and output some element, group element y and some string. For this algorithm A, there should be a polynomial time structure that takes exactly the same inputs, including the same coins, and produce the same string and some exponents C1 up to Cn in such a way that y is equal to the product of the x raised to the power of the c's. This is a quite reasonable restriction. In fact, all non-constructions of structuring preserved schemes have algebraic algorithms. And this restriction was also used to prove some lower bounds for signatures and commitment schemes. And finally, I should clarify some recurring question. This is not the knowledge of exponent assumption. The knowledge of exponent assumption is a security assumption. So you have this security assumption, and then you build some things based on it. But if it turns out that your base is not solid enough, then you have some problems. Or maybe your constructions will be completely broke. In the case of algebraic algorithms, this is a limitation of the current techniques. So you have the preferred way, which is used to obtain some goals, which in this case is building structuring preserved schemes by using algebraic algorithms. And then the impossibility result basically says that this is not possible for some primitives. This points out one direction that designers should not follow if they want to obtain these primitives. If they want to further investigate the possibility of building such primitives, they should take a look at non-algebraic algorithms, as they are the alternative way. And if it turns out that they can build some structuring preserved primitive using non-algebraic algorithms, that's great. I mean, they didn't lose their time looking at these algebraic algorithms, and we have a solution. So let's come back to the result. We consider some primitives that have computation, proof, and verification algorithm as before, and we prove the following. If the scheme is structured preserved and have algebraic algorithms, and the discrete log problem is hard in the source groups, then if it met the probability and uniqueness requirements, this already implies that the output is predictable. For simplicity and clarity of presentation, in this outline of the proof, you only consider the symmetric setting and inputs and outputs that are a single group element, but this can be extended to the other case as well. And the proof is basically divided in two steps. In the first step, use the provability, the uniqueness, the fact that the algorithms are algebraic and the scheme is structurally preserved, together with the fact that the discrete log is hard in the source groups, in order to prove that the output should have a very specific format, meaning y should be equal to g, the group generator, to the power of a constant a times the input x to the power of a constant b. In the second step, we basically say that if the output has this format, it's not unpredictable. So for the first step, let's fix the public key and the secret key and consider a random group element x. Since the algorithms are algebraic, the output should be equal to the group generator g raised to the power of a function a of the secret key and of the input, times the input raised to the power of a function b of the secret key and the input, where these functions a and b can be computed using the structures. And in a similar way, the proof should be equal to g to the power of a function u times x to the power of a function v. So for this fixed x, let lowercase a denote the output of the function a, and b the output of the function b, and so on. For this set of structured exponents, this induces one quadratic equation in each parent product equation, in the exponents of each parent product equation, where the unknown is the logarithm of the input x. If any of these equations is non-trivial, you can use this to break the discrete log problem in the source group. So they should all be trivial. So now considering the values from before, and let's consider another value x prime. And let's compute y prime as g to the power of a times x prime to the power of b, and p prime is the product of g to the power of a times x prime to the power of v. But since all polynomials in the exponents of the parent product equations are trivial, and due to the way we define both y prime and p prime, and the restrictions that we have in the verification algorithm, we should have the result of running the verification with x prime, y prime, p prime, and the public key is equal to running it with x, y, p, and the public key. But the probability requirement basically means that running it with x, y, p, and the public key should return true. So the other one should also be true. But since we also have this uniqueness requirement, for this x prime, there should not be a different y star and p star that would be accepted by the verification algorithm, since otherwise it would break the uniqueness. But the probability requires that the result of running the computation on with the secret key and x prime should have a valid proof. So it can only be g to the power of the constant a times x prime to the power of the constant b. But now, if the output has this format, if we know two inputs, x1 and x2, and the corresponding outputs, y1 and y2, then we can compute the output corresponding to x3 that's equal to x1 squared divided by x2, simply by compute y1 squared divided by y2. Here we have that one term g to the power of a in the numerator cancels out with 1 in the denominator, and everything's are fine to obtain the correct output of the computation. So this cannot be unpredictable. So let's take a look at the implications of this theorem. The three properties that cannot be simultaneously achieved according to the theorem are exactly the ones that we should have in the verifiable unpredictable functions. So they are not possible. It also trivially includes verifiable random functions. In the case of unique signatures, we don't have a proof algorithm, So this is equivalent to a proof algorithm that always output an empty string, and the computation algorithm is, of course, the signal algorithm. And the uniqueness and the probability requirements are the same here, and they both together imply that obtaining a forgery for the signature is equivalent to break the unpredictability of the computation. So they are not possible as well. So for pseudo-random functions, they normally don't have a verification and proof algorithms. But in many applications, they are used together with non-interactive zero-knowledge proofs in order to prove the correctness of the computation. In this kind of combination, we prove that it's not possible to have algebraic structure-preserved constructions for pseudo-random functions. And also for deterministic encryption, there is no algebraic structure-preserved scheme for which the correctness of the encryption can be verified using non-interactive zero-knowledge proofs. And even if we consider the non-strictly structure-preserved setting, where the target groups can also be contained in the public key and the outputs, we have some impossibility results there. So basically, for the asymmetric setting, we can extend the impossibility results. On the symmetric setting, if only the public key have target group elements, then we can extend the result as well. If both the public key and the output have target group elements, then we can show a set many restrictions on the type of operations that can possibly lead to some unpredictability. And to sum up, I would like to repeat the main points. So algebraic structure-preserved verifiable unpredictable functions, verifiable random functions, and unique signatures are not possible. Algebraic structure-preserved pseudo-random functions or deterministic encryptions combined with non-interactive zero-knowledge proofs for prove the correctness of the computation are also not possible. Even in the non-strictly structure-preserved setting, there are big restrictions. And one possible workaround the impossibilities, of course, to consider non-algebraic structure-preserved schemes. And maybe it's possible to obtain some one-time structure-preserved primitives. Thank you for your attention.
Just want to thank all the speakers and all the attendants, and Mihir and Daniela again, and everyone for making it a great experience. So thank you all.